All right, let's take a look at Level 2 Apprenticeship Introduction to Hydronics Session 3. This section will focus quite a bit on the piping layouts of different systems, maybe how they work, as well as some of the flow measuring devices as well. So let's get started. All right, so some of the objectives here: identify various hot water system piping systems, terminal devices used, characteristics of the 1 and 2 pipe systems, hot water zoning systems, and then we'll look at other terminal devices that are in there. So we'll get it started. So the first area we're going to hit up on is specifically 1 and 2 pipe systems. So the 1 pipe water systems, they're primarily used for hot water heating. A 1 pipe system could either be, as they're saying, a series loop system or a single loop type system. We'll take a look at that. The 2 pipe systems, they're generally going to be more of your commercial applications. They've got terminals that are connected across from a supply and return system that allows you to either have it could be piped up as either a direct or reverse return system. And we'll talk about those and we'll look at those applications. So additionally, a continuous run of pipe from the supply connection to the return connection is one of the characteristics of those systems. All of our hot water system flows through all the terminal units. So that would typically be in your series system, okay? And neither the flow nor the temperature of the water can be changed without affecting the whole loop. So what you do in one of those units will be what we do in the other one. Inexpensive to install. It's pretty simple. It's nothing fancy about it. The downside of that is if it's not designed right and you end up with too low a water flow, those first units will typically heat up pretty nicely and maybe even a little overheated, but the last units are where the problem is going to be. They typically don't get enough heat. And so we'll take a peek at why. So this particular system that we're looking at here is what we would consider as a series loop piping system. And as you can tell, we're going to get my highlighter out here. And as we leave the boiler system and we go through the pump and pump that out into the system, in this case we happen to have exactly 2 zones. So we have one zone going this way, we have another zone going the other way. So this first unit, I'm going to switch this over here. The first unit here, let's say we put a typical temperature out here. Everybody starts out with 200 degrees right at the very beginning, this way as well as this way. But then after every single unit, you're going to see a progressive drop in temp. So it's going to start to get cooler and cooler and so on and so forth. Now, we're not talking major, but if it's a properly designed system, you typically would expect to see at this point, after you get past the last unit, you're expecting to see approximately about 180 degree Fahrenheit water. That's only a 20 degree difference in temp. Now there are some systems out there that you could have it where this system could be not 180, but it could be 160. Now we're looking at a 40 degree difference in temperature between that loop. The problem is if that is 160, the temperature of the water going into here may be as low as, 165. So you're starting at 165, 170-ish in this area. This last terminal unit, whatever zone that's in, they're going to struggle with that one. They're going to struggle with the inability to get sufficient heat out of this unit. So this typically end up being a cold room. And that's a legitimate problem. The only way that you're going to be able to fix that is you're going to need to have either a bigger pump to handle that, or we're going to have to properly balance the 2 systems out is what we'd have to do. Now, balancing the systems out it's only going to work if we've got the ability to balance the system out. So on this system, let's say that I'm starting with 200, and as I progress through here, let's say that I'm down to 195, 190, 180, and finally down to let's say 175 on this last unit. So this one here is at 175. This one we'll say is at 160. We've got a balancing problem. So what's going to happen is there'll have to be a balance valve on the return side of each of these loops. That would be ideal. The balancing valve is going to allow me to tweak that side that is the warmer of the sides, this one. So this one, I would keep that open. This one, I'm going to have to close down. So what I need to do is somehow make this loop, and I'm going to call this loop number 1. And this one I'm going to call loop number 2. I need to somehow be able to get more water flow through loop number 1. Now, if this loop number 1 is at 160 and loop number 2 happens to be 175, what I'm going to do is somehow try to get this one more restricted. The one at 175, that becomes more restricted. When I do that, it slows the water flow down, and you'll start to see the water sitting in these baseboard a little bit longer and these heat emitters longer. As they do that, you're going to see this one maybe change to 193. This one maybe is now 186. This one here, maybe we're down to 175 coming out of there. And maybe in the end, we end up seeing this loop right there ends up being maybe approximately, maybe it finds a sweet spot at 170. So the goal as I do that, as I am being more restrictive on loop number 2, you will typically see this loop number 1, that temperature, instead of being 160, that will then push, this pump will try to move more water through here, which will then, of course, take this 160 and increase that, and maybe that ends up finding, hopefully if we balance it out correctly, it ends up finalizing at 170 for each of the loops. And that would give us a very proper balance for the two circuits. Typically when we're balancing out systems, that's how we want to do that. We want to tweak it so that each of those ends up having the same return temperature when everybody's calling and their loads are appropriate on there. And that's how that's typically done. And that's a basic series system. This one happens to be 2 zones on this one. It's very possible you could have one thermostat for the whole system. As it's shown here, they're not showing any zone valves, but in most cases, that's what people would primarily do. So in this case, so a single loop system, in this case here, you got the main supply with all the branches, all the terminals, small piping in the branches, smaller than the main. So you might have a 1 inch, 1 1/4 inch, or whatever bigger size piping that you might have. And then as you split off to the branches, then it ends up being a smaller loop. So in this previous one, it would not be uncommon to see the piping here would maybe be a 3/4 inch loop. This one might be a 1 inch or a 1 1/4, depending on the BTUs that we're extracting. But most likely a 1 or a 1 1/4 for a little system like this. And this one would also be approximately about a 3/4 inch loop. A good rule of thumb that I like to use is if it's, anywhere from, let's say, 15,000 BTUs per hour or less, I prefer to do that with 1/2 inch pipe. If it's more than 15, up to maybe 40, 50,000, then we'll go, so I would say 15K to 40K, 40-ish K in that area, 1,000 BTUs, then I would go 3/4 inch on those loops. And it's a lot of that is dictated based on your, obviously you got to do the heat load for the building, and you know what the zone is, then you can figure out that it's really all based upon the water flow. So 15,000 at a 20 would give you about 1.5 gallons a minute on 1/2 inch. That's pretty decent. And if you can do, and then anything more than that, you're going to have to use 3/4 inch for that loop, and that'll go up to about as much as maybe 4 to 5 GPM would be about the most you're going to get out of a 3/4 inch pipe in most situations. So, all right, there is another one that we can take a look at is in this particular case. So this one here, we're talking about a one pipe system in this particular case. And one of the things that we're going to have, and I'm going to go to this picture just to point this out. This picture, what we're looking at here, is indeed the one pipe, what we call a one pipe main system. Now in this particular system, we are also showing this as having 2 runs going each way. So this is the supply system. We branch off and venture to this way, and we go to this way. Very likely and very possible they potentially could have it where there might be a zone valve potentially here, and there might even be a zone valve on this side potentially. There's a number of different ways that this could be done. I don't anticipate and expect to see many people putting a one pipe main system in for a couple of reasons. So in this presentation, the other thing that I'm going to point out here is the hot water supply is going to be delivered from the single main loop, and each of those loops are going to then have a supply input and return that's going to go from the main back to the main, and you're going back into the same pipe. And you have to have generally the way they do this is they'll use a special, what they call a diverting or a one pipe main tee, or a one pipe fitting, or a diverting tee. There's a number of different monoflow tees, or a monoflow fitting is a Bell and Gossett term for their particular tee. Either way, they all make them, whether it's Taco or Bell and Gossett, they all make that specialty tee. So it's supposed to be, I see it as more of a, maybe a bigger at residential job or a commercial industrial type heating system. I don't expect anybody to be putting these in for the most part, just because of some of the issues. So the book or the author describes this as having better performance than a series loop system. Now, I would actually beg to differ on that one. I don't know that that's necessarily the case. They do have some challenges, and one of the big challenges that you face in there is getting the air out of those loops. So remember what I told you earlier. I said here's a main loop. So I grew up with one of these systems, and the way that we had this, I'm going to switch it over to a highlighter here. And the way that this ends up working is you'll have that warm water coming out of here, and then you'll have this pipe here oftentimes ends up being, let's say, a 1 inch, or it could be even a 1 1/4 inch loop. And every one of these will be either 1/2 inch or 3/4 inch loops. And they basically are feeding directly from the main to the terminal unit, and then they feed back into the main. Now, you'll see that by the drawing. So that means that you either have to have a T here, basically a monoflow T, or a one pipe fitting T here, or in both places. And it's one of those where when you have to pipe those, if you ever are in that position or you have to service an account that has one of those, you might want to consider looking at watching for those little specialty rings. So they basically have a section or a part of that T that has to be in between the terminal units. So if that's kind of the way that that's really set up on there. I'm going to just point this out. So in a monoflow T, there's going to be a part of the T that will be identified as having a ring. The rings are always go in, they will always go in between the terminal units. So that's something to watch for. So kind of what happens here though is you bring that warm water, and you bring that warm water into the first terminal unit, and then you probably will have some sort of a little balancing cock on the outlet side of this thing. It'll go back and it keeps feeding in it. So where the problem that I see this as is that every single one of these units, every one of these terminal units is extracting BTUs. So you're still very much like a series loop system. This is progressively getting colder. So I don't know exactly why they would deem this is a better system than the other units. There might, maybe one advantage is maybe they feel you can run a little bit less restrictive circuit, or maybe you can run a little bit bigger system, and which you can, but compared to a series system. But I think the advantages are far outweighed by the difficultiness sometimes of being able to extract air out of each of these terminal units. So without that monoflow T that's identified here, there's no way you're going to get the water to want to scoot out through here. So what determines really your water flow through these branches is primarily the amount of resistance in this spot right in this area. So if you can create resistance by saying we're going to force some of the water to go up through the terminal unit, some of the water goes up into this terminal unit, some of the water scoots through here, some of the water comes back into here, and we feed it right back again. So then every single unit that's further downstream is still getting colder water. And so it's really just it's kind of a more advanced series system that it maybe allows you to get a little bit larger or a bigger system. But other than that, I don't see it as a big advantage of it. I think there are some advantages, but I think they're really outweighed by the inability and the difficultiness of trying to get the air out. So same thing applies on this side of it. We scoot through here, go through here. We've got some. So these specialty Ts, what they're really doing is they're creating a little bit of resistance in between these that are forcing some of the flow to go through these circuits. So there again, that's a one-pipe main system. Let's take a look at a two-pipe direct return system. Now, a two-pipe system is going to be more of a commercial type application. This is really the ideal way to be piping systems is two-pipe, not necessarily in direct return, but in reverse return, and we'll talk about that one in a little bit. So the supply and return water, they're going to flow in opposite directions on these systems, and we'll take a look at how this system is set up. So let's take a look at the details here. So one of the things that's going to happen here, I'm going to go back to my, I'm going to go to my marker on here, and I'll use the orange this time. Whoops, wrong one. Let's try it again. I'll use this one. So what is happening now is my supply, or the first unit supplied in here, ends up going, this pump will supply it. Now watch what happens. This first unit that we're delivering in that main system that one is going to be a very low resistance circuit as a rule. So this one tends to want to short circuit because that's really where, let's put it this way, that's the path of least resistance to go right through here, right all the way back into the boiler. So having this one balanced out is going to really be the kicker here to get that to want to go. So there has to be some sort of a restricting balancing valve, obviously, in every single one of those devices. Now, we can still have control valves, and whether it's a two-way or a three-way, absolutely, that would be in each of these returns or supplies. Either one of them would work, but that's really where it is. So the path of least resistance is right here, and we work our way. Now this supply, keep in mind, keeps on running, and we feed to the next unit. And then as long as there's a demand, this thing will call. And again, typically, you're going to run into it where there are zone valves that would be in each of these things. So definitely that's the case there. So what you find is that the units here end up getting, if it's not balanced correctly, this one will get less flow, this one will get a little bit more, and this one is going to get the most flow. That's the dilemma that you have. So the balancing on these is kind of tricky. Now, commercially, they use a lot of these direct return systems because it's a little bit cheaper to pipe the system. But are there any advantages? What are our advantages? Well, I think one of the advantages is that if the boiler water here is 200 degrees Fahrenheit, and let's say that this one ends up being 180, okay, very realistic on a commercial job. Every single one of these units, everybody gets the same water temp. Every single one of these gets 200 degree water. So in a commercial job, it would make total sense why they would do that. This way you're delivering the same water temperature to all of these air handling units in a job that might be spread out very far. So in that case, within reason, you're getting the identical water temp, and then it's a matter of being able to balance the system out. So that's pretty much the way all of these jobs have to be. So a couple of things that I just am going to highlight here, and in this case, so I talked about circuit balancing valves are often needed. You got to balance them out. You got to make the pressure drop. Imbalancing of the system is going to really create some problems with that system. And that's the biggest disadvantage of that direct return system. It's a little bit tricky to do that. And obviously, that's probably that's really the biggest challenge on here. There's some advantages, but that's the challenge. All right, let's take a look at a reverse return system. Now the reverse return system oftentimes is referred to as let's call it a self-balancing system. And it should be used more often than a direct return system. The textbook identifies this as being used more often than a direct return system, and I wish that were indeed the case. Talking to a lot of the engineers in this particular area, they tend to push more of the direct return system, and this is cost driven based on the cost of doing the piping is primarily how they do that, even though it's actually a better system. So the fact that they identify it as a self-balancing system is, we're going to look at exactly why that is. So here they talk about this being, the supply water going to the first terminal unit is the last one returned to the boiler. That makes sense. Let's take a look at it. So when we leave this particular boiler system and pump, we're going at 200 degrees. Now we feed this first unit. Now this one, because this is the shortest run right there going to that first terminal unit, this one has the longest run for the return side. That's what makes it self-balancing to some extent. You're still going to put a balancing valve in the returns. You're still going to, in each one of the returns on the terminal units, this one will get a balancing valve here, this one will get one here, this one will get one here. The control valve could be supply or it could be the return, either way of them. Everybody gets the same water temp. It's a very nice system. This is really the ideal system because everybody gets exactly the same water temperature. It's just that you're running, two pipes. But this is typically the way that you'd like to see all of these systems done. So that being said, if you think about it, this whole return system now, the return where it starts at is primarily only going to give you approximately, if this right here ends up being, let's say this one ends up being 180 degrees Fahrenheit, and maybe it's got 2 GPM. So that means you're going to have 2 gallons a minute on that loop, and then when you pick up this unit, maybe this one's got 3 GPM as an example. So what happens now is then this pipe here has to carry now 5 GPM. So what happens is it ends up getting progressively bigger. So it ends up being very small there. It gets a little bigger, maybe a little bigger, and finally, by the time it goes back into the return, you're carrying all the water from every single terminal unit. So nice little system on that reverse return system. It's really the ideal system. You'd really like to set them all up that way. A lot of systems get recommended that you do indeed pipe them that in a 2-pipe or in a reverse return manner. There's another system that we utilize a lot, and if you're dealing with any new construction, there's a very good chance that somebody might be using a radiant floor heating system. And the purpose of that is the fact that now I can use probably some PEX tubing embedded in the concrete floor, and I can utilize, take advantage of maybe a condensing environment potentially that would allow me to have very low water temps, achieve very high efficiencies. And again, those are typically done, we'll set up manifold systems with a supply and a return manifold and, pump it out, pump it through the system accordingly. Typically, these types of loops in here, usually you're going to limit to generally not more than, I would say not more than 300 feet in length. If you do longer than that, it ends up tending to usually be too restrictive. And of course, this is depending on the flow rate that is required. But there again, if you've got a large enough space, you're probably going to need enough flow rate. So typically, we don't generally want to run more than 200 feet. And if at all possible, you're going to have it where there would be many, many loops that would be coming out of there to and from these things, so as opposed to one continuous loop. So it just depends. These types of systems really need to be laid out and planned out to make sure that we have the right lengths of loops and what water temps. So they can be unbelievably comfortable for the system, but they have to be properly set up and designed on there. So that is what is needed. Here's a good example of this one here, showing the PEX. Now this one over on this side here, it's an awesome little fast track system where these little grids are popped into there and you'll snap all that in there. It's really, really nice. It's a nice way to lay it out. An alternative method, and this is what I've done on my own systems, is I've used the plastic staples in there. So I have these foam staples I'll put underneath my slab. I'll put all of the foam insulation on there, and even notice on this picture, I want to point this out, you're going to notice on this system how they have insulation on the edge of the concrete. That is really imperative. This one here also has it. This is what we call edge insulation, and the edge insulation is very necessary to prevent the loss of heat that would go directly into that wall and straight down. That really should be done in many of those systems. So but you have to, like I said, the heating contractor usually has to push that, or it has to be in the specs. Otherwise, the mason contractor is probably not going to do that, as they wouldn't know enough to do that in most cases, unless that's their primary method of doing that. But very, very nice system. So nice little section in there. The one other thing I was going to point out here as well is, and I don't totally know on this picture what this is being done, but you'll notice right in this area where they have that piping. So typically what we try to do is we try to run our PEX tubing away from those little areas. And if this were, let's say if that happened to be a toilet, you would not want to run your tubing too close to that toilet, or you'll have problems where the wax ring from the toilet will actually start to melt potentially. So that's happened in some applications, especially if the water is warm. That'll create a problem, and you'll have a leak in the toilet. So just something to be aware of. Zoning. How about our zoning with valves? So here's another system here. So A system that uses zone valves, usually only have one pump provide hot water heating to these zones. So in this particular case here, you would have, in this one here, what we're showing is we're showing a circulating pump that would be identified right there, okay? And this one here has a loop that, let's call it the supply manifold right here. And what they're doing is they're delivering water to each one of these zone valves. So if there's a demand, these zone valves will open up. And if any one of those opens up, generally this pump will then be initiated or energized to allow, hey, we need to get water flow, we need to get it moving. So that's typically what will end up happening. It would be advantageous and it would be a very good manner to have a variable speed pump for this system circulator when you have multiple zone valves that are going to be used in these applications. The biggest reason is that when only one zone calls, let's say zone 1 calls or zone 4 calls, the pump isn't trying to push all of that water flow that it possibly can through just the one zone. A lot of the more advanced pumps, like the ECM pumps, have the ability to recognize that only one is going, and what happens is when only one zone is going, what will go on is it'll try to push too much water through some of the respective zones. In the new ECM pumps, those particular pumps will recognize that only one zone is going because it'll recognize the energy consumption by the pump, and it'll actually slow the pump down so that you really only get the proper amount of water flow in here. It's really a fantastic system on there. So I would encourage anybody to study more on that if you're it's something you're really interested in. This one here is in this system, it's really nice. We've got a boiler system. On our boiler system, we're showing an indirect hot water tank. We're showing a combination of some varying zones, different types of setups on here. It's really a nice setup. This system is also piped. I want to point this out. This one is actually set up as like a primary, secondary type system. So you'll notice that there are two T's here and here that are spaced very close together. Now those two T's are such that that'll allow this boiler circulator to turn on or be energized to pump the water into the boiler and go through the boiler and back out. So you're going through the heat exchanger and then back out and back into this loop. Now the advantage of this is that allows you to do a post-purge on your boiler system. So when our heating demand is done in the boiler and you shut that boiler off, that allows the pump to kind of pull and extract some of those BTUs out of that boiler system to be just a little bit more efficient. And that's a really good way to do that. On this one here, they're also identifying, with the indirect, they're also showing me a domestic water circulator that is going on there. So a lot of good things that are happening on this particular application. Very, very good system to utilize for our hydronic systems. But lots of nice stuff in here, a lot of great things. So certainly as an alternative method to this, one of the things that I'm going to point out on here is the same scenario as the previous system that we just looked at. The same scenario as this one, where they have a primary secondary system. They are having this pump in what I'm going to call as the primary loop, and it's going to deliver water to these zones respectively, whatever it needs, whichever one is calling, however that might be. And then they return back into this return loop. So absolutely every single one of these loops is going to need some sort of a balancing valve on the return side, and that's standard practice in the industry. Everybody would need to do that. So on the zone circulator application, what is different here is you'll notice how we no longer need this pump. It is the main pump that you saw in this example, called the system circulator, is replaced by zoning circulators. And every one of these zone valves, you're going to notice, has a check valve at the discharge side of that, which would be very appropriate. This is a very nice system, provided that it's done correctly. Otherwise, it ends up being kind of a big energy consumer if you've got a bunch of pumps that are pulling a lot of energy. So the ECM pumps really can help with some of that. And but yeah, very interesting system. The other thing that also is interesting on here is that you have to have, with this piping arrangement, you've got to have the ability to have an air purging system. So this little combination of a valve, a shutoff valve here, and a boiler drain here allows you to purge the air out of those loops when you have to do service on each of those. So you'll notice that every one of those has that. Everything else down in this region is very much the same for either one of those two systems that you have to be aware of. But there again, you just have to kind of watch that to see how that is. I think what usually, one of the things that I usually look at for the zoning pumps, if I'm going to do zoning pumps, and maybe I find that, I just don't have, the zones are big enough, maybe I, with all these zones, maybe I just can't get a pump reasonably priced that's big enough to do it any other way. This is a very, very nice way to do it, where I can just do it with zoning by pumps in there. So it is a nice system. Just, it's a decision you have to make, what's going to be most cost effective on that system. So that's very interesting, very, very typical on here. The other thing I want to point out is I want you to look at the placement of the air separator and the expansion tank. And you'll notice on this system, they're putting it on the inlet side to that circulator for those, what I'm going to call the primary loops or primary pumps. If you look in this previous one, you're going to notice that the piping arrangement is such that the expansion tank and the air separator are just prior to the system circulator, again, the primary pump. This boiler circulator ends up actually being a secondary pump because it's pulled off the main loop. You may or may not have a differential pressure valve on here. That's something that is really not needed if you are using pumps that are not excessive in head, and you can provide a sufficient flow to the remaining zones effectively. That's really where an ECM type pump has a big advantage over a conventional high head pump. There again, your pump selection really has to be spot on these things to make them work right. So let's take a look at some of the terminal units. So we have terminal units that are, obviously their job is really to transfer the heat, from the main water supply to the zones. And we've got a few different types: convectors, baseboard, radiators, unit heaters, ventilators, fan coils, and duct heaters. So let's take a look at these. So first of all, convector heating terminal. These, a lot of times they will depend on gravity conductive heat transfer, meaning that they're going to take the colder air that's on the floor area, and they're going to move those through and over the heat exchanger to allow you to transfer heat out of them. Now, that's one way to do it. So they don't typically have a fan. That's usually what happens is with convectors. Now, they'll have a fin tube coil that's going to be in this enclosure that will be kind of usually recessed in a wall, but it doesn't have to be. And those are typical ways that they'll run that. It's a very simple system. You can put a valve in there, which typically would happen. It would be controlled by some thermostat. And again, not probably your highest end type of a heat emitter, but very effective for handling. A lot of these convectors are put in like vestibules and things like that. But I've seen them in just regular rooms and hallways as well. They will be totally fine. Again, near outside walls typically would be ideal where you'd want them. Baseboard units. Well, normally we would install baseboard really on where the heat load is, which would typically be near that outside, where an outside wall would be. That would be typical, where you might as well put the BTUs where the heat is really needed. Most of the baseboard units also work on convective heat, very much like a convector, like the previous convection or convector heating units. They typically would do that. So again, usually natural convection in most cases. In a series system, which a lot of your residential jobs are going to have, they typically do have a series baseboard, several baseboard units that would be put in an application. Again, rule of thumb, one little notable fact I would say is typically we're going to have approximately around 600 BTUs per hour per linear foot for baseboard. And again, this is assuming that you're running approximately like 200-degree water through those baseboard. Anything less than that, this number goes down. You just have to be careful with that. That I've seen this number be anywhere from 500 to 600 BTUs per linear foot. A lot of that is dependent on your water temp, so be careful with that. Here's an example of more of a higher end commercial thin tube baseboard with a big enclosure that's typically done on there. Again, in commercial applications, they make these 1 inch, 1 1/4 inch. They make them bigger, they make them smaller. You just have to find the right application. So radiators is another type of a heat emitter, and they're mainly designed to work. Yes, they do some convection, but their primary source is a big type of having a lot of surface area and radiate that heat to the cooler areas. A lot of your older cast iron radiators that you might have seen in older buildings or older homes, it's very nostalgic. People really like to have them, and they're, again, if you ever watch an old episode of This Old House, you probably see on the East Coast there's boatloads of these. But there's a lot of people around, some of the bigger areas that they really like the looks of that old style. And you can even still buy them today for those customers that like to have that. Here's a good picture of an old cast iron radiator that would be in there. There's a lot of value in these things. They look pretty neat on those. So you'll also see the angle valve that's on here. That's really their control method in there. On this other end, you'll also notice a bleeder. Sometimes these were, a lot of times they were originally used in a lot of steam systems. So that's kind of a neat little system. Very, very pretty type of a system. Let's take a look at unit heaters. So on a unit heater, typically we think of as like a propeller fan. Doesn't have to, but typically you would see something used in a commercial application or a residential application that would be mounted somewhere near the ceiling. Has a heat exchanger. You got a fan that blows the air over that. Every time there's a demand, the fan turns on and it blows a bunch of heat in there. So it's a neat little system. Generally, you're not going to be using this as your primary, you might be your primary heat source, but you're not going to be putting this in your main living space. This is something more of lower, it tends to be sometimes a little more drafty, less comfortable, but usually, like I said, in commercial jobs, they'll use it as, they don't want the room to get any less than maybe a certain temperature. Again, pretty basic that they'll see. There are a couple different types of unit heaters that are out here too. So we have units that are what they call horizontal unit heaters, and what determines whether it's a horizontal unit heater is the direction of the airflow. So a horizontal unit heater would blow the air in a horizontal direction, leaving the unit. A vertical unit would typically be, where a lot of them that I've seen that have done this, they'll have a round type unit. They'll have a propeller fan that would essentially take the air and either draw it through or blow it through, but typically they're going to blow it down, and then it'll fall directly on the occupants in those particular areas. And you can put blades in there that'll divert it out there, but again, that's really what you have to do. And it makes total sense. Vertical units, to use them on a high ceiling area, that would make all the sense in the world. And then a horizontal unit, if you got a low to medium ceiling, it makes more sense to do that. And again, it just depends on the application. So here's an example of 2 units that would be considered definitely a horizontal unit. Little resonator on there, neat little system. And those are typically what it is. There's, again, this is by far the more common to see applications like these, like the horizontal unit heaters in applications. So neat little system. So hot water coils in your air ducts or your VAV boxes, again, very commercial when you're starting to talk about these applications. In the northern climates, you typically see a lot of hot water used. In the southern climates, you typically see much more electric heat used and not the hot water. And again, the hot water systems by far are more efficient over the electric side of things, but there again, you have to kind of recognize or look at what they're doing. Hot water in and out, obviously to a VAV box, you could have a 1-row, a 2-row coil, and again, it's the amount of heat that's needed is more for supplemental heat to because commercial jobs oftentimes, especially VAV, most commercial jobs are predominantly cooling, so they will normally be reheating that cooler air that's blowing in the duct. So typically these are going to be used, you'll typically see these more used in the external areas around the outside of the building, the exterior, I should say, of the building. So you're certainly the interior. And obviously the valves, you're going to have control valves are going to have to control how much water goes into those applications. And most of the time you would have some sort of modulation, but it doesn't have to be that way. Again, just basic fan coil. Here's a very good example, a nice picture showing a supply and a return system. So here we're taking my supply, we're running it through a coil, and then back out into the return and on its way out there. So the air would then make its way this way. It would go obviously over that coil and supply warmer air or tempered air into that. So very, very common in our northern climates. Nice little system. All right, so let's take a look at this section. And first of all, we got a water piping system, which all the hot water flows through all of the terminal units, will be considered as should be a series loop system. And the next one, to prevent the pump from deadheading in a zone system. Now this one we didn't talk a whole lot about that, but there's a couple of things that we would do. Deadheading is a term that we refer to as when the pump is running, but there is there's no place for it to go. You've deadheaded the pump. So to prevent that from happening, a lot of times they'll use these differential bypasses to kind of fix that to some extent. So, but there again, commercial systems, they have gone away from these differential bypass valves, and they've gone to more of a variable frequency drive system that they will slow the pump down. In the residential side, we have ECM pumps that are available now that actually control head. So this differential bypass valve is really something that is absolutely not needed, and it shouldn't really be used when it's unless it's absolutely necessary. So there's other things that can be done. A vertical unit heater is best applying in areas that would have you might remember this one, should be something with a high ceiling, okay? Very high ceiling because you're blowing air straight down, and so a high ceiling air would make the most sense. And that is section 3. So we are going to break this one up, and we'll move into section 4 and break this up.